This session is on software. I get to grab the first 7 minutes of that to chat with you about some recent work we've been doing, and then we have a series of other speakers talking about various things. We're going to do a quick screen swap partway through because I'm going to switch from an ARM Morello box to more conventional hardware. So, anyway, thank you very much. I'm presenting joint work, a number of people at the University of Cambridge, SRI International, and then various other collaborators around library compartmentalization. I'll explain what that means. So, there we go. So as you're probably aware, but I'll explain anyway for this audience, software compartmentalization is really about what many people think of as software sandboxing. When you take out your phone and you're running an app and you don't automatically have access in that app to every text message on your phone or every entry in the address book or every photo that you have. And if you take out a contemporary phone and decide to send a photo, your phone is going to go through some process, usually largely invisible to you, by which access to those photos is authorized. And this idea of software sandboxing is very powerful. It's been very effective in mitigating vulnerabilities and software supply chain attacks. But it is an idea that can be taken much further. It's possible to isolate much smaller components of software and give them many fewer rights. And one of the key goals in the design of CHERI was to enable that kind of programming paradigm. And I have sort of sketched at the top of this slide an idea about this, which is, you have a presentation package. It's made up of a slide deck. The slide deck has many media elements that you have pulled out of Google image search or wherever else you got them, slides from your friends, probably slides from your enemies, etc. And when there are vulnerabilities in that very complex piece of software, your presentation package, what exactly should the attacker get out of that? And the answer that we have is as little as possible. Ideally, access only to the bad image that they sent you and no more. And the scalability limit we see with current hardware designs is that as we try to expand the number of processes based on MMUs or using other techniques, we really run out of steam quite quickly. And it is completely fine just about to have every tab in your web browser run in its own compartment, but try processing every image in your web browser in its own process on top of a Unix system or a Windows system. That experience is extremely uncomfortable. We won't demonstrate that for you, although perhaps we should prepare a demonstration someday so that people can see what that's like. So the claim in CHERI is that we're going to allow you to have many more of these compartments. We're going to allow you to create and destroy them much more cheaply. We're going to allow you to switch between them much more cheaply, and that they'll be able to share data more efficiently and in a more programmable way. And both of those are important parts of the argument for CHERI. So we have achieved in casual software demonstration at least 3 orders of magnitude compartmentalization beyond what is currently supported in today's hardware designs. I think it's quite plausible to do much more than that. We just have yet to find that many compartments, and that is part of what this talk is about. So there are different models you can use in CHERI to say, what is a compartment? Is it shaped like a process? Is it shaped, well, one we care about a lot, shapes compartments around libraries. It isolates libraries as software engineering units. So the principle, for those who don't know, of a software library is that it is a collection of code and probably some globals and things like that, usually originating from one-ish vendors that perform some sort of collected set of functions. So in your device, zlib or libc holds decompression and compression logic, and your libping contains understanding of how the ping file format works. And in fact, if I pull up our Chrome web browser, we'll see that there's about 700 to 800 such libraries loaded during execution, which contain all the different kinds of data processing logic to handle, and connection handling and protocols and all that stuff. So one of the models we've been exploring is placing these libraries into their own compartments, basically saying, okay, well, each library can run with limited access to global state and limited ability to manipulate control flow globally. And that is going to limit the effects that a vulnerability might have, especially a vulnerability that gives us arbitrary code execution. And there's various bits of state that are relevant. It's the globals, it's the functions, it's also interactions with the OS, it's residual stack memory, all kinds of vastly less exciting things, but all of which are tools that attackers use to gain privilege. When attackers are trying to achieve arbitrary code execution, unless they're having a very good day with a software supply chain attack, they're going to be using the tools that are left around inside some compartment, the pointers that are there, the data that is there, the ability to influence control flow and so on to get this arbitrary code execution. So in the library model, one of the goals in shrinking down the set of available resources, especially code, is going to be to limit the tools that are available to attackers. They're going to have fewer gadgets. They're going to have fewer pointers that they can potentially abuse or otherwise use to gain privilege. Assuming that they do get arbitrary code execution, a compartment is going to limit the set of rights they have access to. They have access to only certain data or only certain other code. And then importantly, I think often forgot, the set of further attack surfaces. So when you're an attacker in a finely compartmentalized system, the first vulnerability is not where you stop. You now need to make your way from compartment to compartment to privilege. And we see this already on devices like iOS, where you need 6 or 7 vulnerabilities to get total control of a device often. And so what we're interested in when we reduce compartment size is reducing those attack surfaces. So you need many more of these vulnerabilities, and perhaps you can't find them. That would be a great outcome. So we've been shipping this model, where we place libraries in compartments, for several years now. And it has proven stable and usable, and it is experimental like so many things, but quite functional. But a problem you get is libraries are, in fact, software engineering units. They're bundles of code that were created because they were maintained together and have common functionality. They are not necessarily good security boundaries. So we'd like to try and shift these compartment boundaries away from library boundaries. We'll keep the library boundaries as well. They're not bad edges to put compartments in and to organize code and all this stuff. But we'd like to be able to say, okay, well, let's take a library that has, for example, some extremely sensitive and historically vulnerable data passing code, and also has some I/O privilege because it has methods that take data from files and process the images and so on, and push them into different compartments because they have very different sets of privilege. And when you compromise the passing code, you should not gain file system access. And that is not supported today on our software stack without breaking your library into multiple libraries, which is a software engineering mess. It changes source code files, it changes build systems, all that stuff. Software engineering boundaries associated with libraries may not be great, but they are things that we have settled on, and perturbing that comes with a real cost inside organizations and between organizations. So the feature I'm going to describe to you is one in which we allow you to break up those libraries much more easily into multiple compartments, and it's an experimental feature that, if we've shipped it today, yesterday, tomorrow, something like that, it will ship in our new version of the CHERI BSD OS. It is a very experimental feature, and yet I think a very useful one. So I'll remind you that the foundation for all of this is CHERI-based memory safety, if roughly speaking, implementing pointers using capabilities, and reducing the rights on those pointers using bounds and permissions and so on, and the tagging mechanism. And that sounds great. We take all the explicit pointers in the language, the implicit pointers in GOTS and other things you don't probably want to know about, stack pointers, so on. We implement them all as capabilities, and we limit their rights. When we do this for compartmentalization purposes, we realize that we can, in fact, do this to multiple pieces of software running in the same address space. And so we can set up different compartments simply by not giving them pointers to the contents of other compartments. We can set up protection domains. We can use these spatial safety, temporal safety features to make it so that information doesn't undesirably go back and forth. We can do more than one of them. We can then do domain transition between them using features we won't describe today, but allow you to effectively jump between them using function calls. And then you have a flexible set of shared resources, and one of the important pictures for CHERI is that sharing is also much more efficient. When we do sublibrary compartmentalization, which is this new feature, what we're effectively saying is that every library mostly consists of a set of other libraries, of individual instances of the resources of the libraries, global variables and code and so on. They each have their own PLTs and GOTS, for those of you who are into those kinds of things. There are some contents which are not replicated between them, string tables, symbol tables, and so on. But they're all, each of these bundles of library content is going to be addressable using the program counter capability. This is an implicitly, not only accesses code, but also is used to reach global variables in current code structures. So when we're running inside one compartment, we're going to have access to its resources, but not to the others. And it falls out very naturally from current code structure and linkage models. And in many ways, CHERI is about linkage as much as anything else. One question you might have is, okay, so what goes in different compartments? How do we figure that out? That is an excellent question. That is a research question. It's a question we should all care lots about if we're pursuing compartmentalization. I will not answer that question today. Instead, what I'll do is describe mechanism that could be, and policy that could be an output from such a process or such a technology that may in the future exist. And there are research programs in DARPA and elsewhere looking at that topic. We're going to have what we call compartment placement. Compartment placement simply says, when you're building something large like libc or the Chrome browser, where do these components go? And because we're taking a very linkage-based view, although we're not changing what your actual library boundaries are, we're very much involved in that linkage process and pulling in the symbols and so on. This is a low-level mechanism. You would not want to do a lot of maintaining of this by hand. We do have a term for this which sounds good, which is engineered compartmentalization. You thought about it and you did it and you hand-encoded it. We write make files by hand in the same way, also an engineering catastrophe, and yet we survive. But I think the ambition here is that you move to some kind of automation to get there. And the automation might be some incredible machine learning thing. Probably it's actually high-level guidance on these bits of functionality, these kinds of pieces together. This core graph needs to go into this compartment. Dear linker, implement that. The second part, which we have not implemented in the current prototype, but we're currently exploring, is the notion of access control. So one thing we've observed is that when you write source code and you also write linkage policies, there's a distinct gap between the two. Compilers don't always generate the use of the symbols that you expect. And also, if you have a software supply chain attack, this specification of the rights of your library, what it's allowed to reach, what APIs it can call, what globals it can access, today you just modify the code and insert system in a funny place, or you use LD preload, or you do whatever supply chain attack we've most recently exercised. With our model, you would have a specification that said, these are the rights this library or compartment is supposed to have. And when the two of them diverge from each other, then you have a compilation failure. So ideally, you're auditing the set of rights as your software changes. Even then, you can also enforce these things potentially at runtime. So we have a notion of a compartment policy, which we have elaborated and explored the idea for, but not yet implemented. This is especially important if you have automated tools or very large-scale software where you can imagine these policies diverging from the software implementation. Engineered policies, as I said, that's what we're doing today. And I thought I'd show you one example of that, another in a moment. But when we take a program like the KDE terminal window, which I'm running behind this KDE PDF viewer, we find about 145 libraries. That's what it takes to implement a terminal window these days. And of those, some are compile time dependencies. There are things that are known, like the GUI class libraries for Qt and KDE. And other ones are known only at runtime. They're actually DL opened as a result of configuration files saying, go find this plugin. So a key requirement for us is the ability to compose all of these policies at runtime and get sensible results. And I think the approach we've taken achieves that, but I think the list of research questions, as always, remains quite large. So what we've done in this example is simply said, okay, well, let's start to break libc out of components. In particular, let's identify some critical trusted computing bases. The memory allocator, for example, and the revocation code hold capabilities that cover a lot of the application address space, certainly a lot of the data that's important. So we want to start breaking that out so that if there is a compromise of libc, you don't automatically get all the keys to the system. And that approach is beginning to be effective. We've not done a lot of this hand engineering yet, but working away at it. So as always, a quick demonstration, and make it very quick for the purpose of timing. I'll take a look at my process list here, and I can actually see my Ocular process. This is the PDF viewer we were just looking at. And I take a look at its compartment list. I can go through, you can see tons of libraries as threatened, but indeed you can see a bunch of these libc compartments. Currently, these are our early experimentation with trying to break up libc. And I can also show you source code, which gives you a sense of how you might maintain these things. So in the FreeBSD libc, which we're working with, there's a series of components. One of them is standard I, and we've basically associated policies with those components. Those components, not necessarily perfect compartment boundaries, but they're starting points for compartment boundaries. So you can see we've gone through, and a bit like a makefile, assigned symbols. We can also do that in much more coarse-grained ways. In fact, perhaps often in preferable ways. The right subdirectory here. Often you find a bit like a makefile. Actually, you just want to say, I've carefully named my source code files and structured my source code files so they align with my compartments. And we find, in general, pretty good alignment between source code files and compartments or subsets of compartments. This breaks down when you work with a really complex piece of software. So we have, for example, applied exactly this approach to the FreeBSD kernel. And there you find, okay, well, you have lots of things which are conceptually the same in a source code file, but their privileges are markedly different from each other. And then you want a non-source code intervention way, a maintainable way to do it. So that is the end of a brief talk on the topic of our compartmentalization work. I will just pull up the conclusions and say, we've put together a sub-library compartmentalization mechanism. It's very much a work in progress. We're learning how to write policies. We're learning how to engineer it. But the mechanisms are there such that you can actually get a very effective result. And we need to go into that place because the software engineering boundaries that exist in libraries are actually not the compartment boundaries often that we want. If we want to make strong claims about security arising from compartmentalization, we have to do the engineering of compartments as a software engineering activity. And this is a necessary tool, though not a complete solution, to try and do that. If you install our new CHERI BSD snapshot, coming out today, tomorrow, I don't know, I'll look at Jessica, see if she nods her head. Is it released yet? No, she raised her hands. It will get out sometime this week, and you can actually give all this stuff a try. It's very, very straightforward to do. So thank you very much.